This is Frame by Frame Season 2, Episode 3. Today we'll be looking at weights and biases along with some activation functions. These topics really feed into each other, so I'm just going to talk about both here. In previous videos, I've talked about how when a model goes through a forward and backward pass, we'll usually have some kind of parameters that we're going to tune. We're going to be looking at the weights and biases specifically. Those two terms sort of go together like
Bills. Hey, what you serve? Bills. Hey, what that is? Shells.
In general, the weights will tell each neuron how much to pay attention to each input, and the bias is going to give a baseline so that the neuron can have the activation start from somewhere, giving it more flexibility. So if we dig a little bit more into the weights, these weights are just scalar values, so you can think of them as like an m value in the equation y equals mx plus b. So these weights represent the importance of the input features from the previous layer. And we're going to be multiplying each individual input by a weight. Either it's going to be positive or minus, and that will represent how strong we want to keep pushing forward that weight into the next layer. You might have an example where we have an edge, and we want to maintain that importance, so we give it a strong positive value, let's say. Now there's tons of weights throughout the entire neural network, but we're going to be changing these weights adaptively throughout the entire training process. And what I mean by that is that as the model gets sent through with more and more data, we're going to be tuning each one of these weights so that the model is going to correctly understand what we're trying to predict and trying to ask of it. And we will be talking more about how to actually change those values in future episodes. But for now, just understand that the network will be changing these weights and biases actively as it's being sent through, or as data is being sent through. And when we're actually starting out with the initial network, we're going to be setting each one of these weights and biases to a random value. If they're set to 0, that's not very helpful. Anything times 0 is 0, and that wouldn't be any help to us. So we set them to random values, random small values, so that they can adaptively change as the model is trained. So the bias term acts as an offset value that we'll have when we add up all the summed values. It's like adding in the b term in the y equals mx plus b. So the bias term will give each neuron a starting point for when we're using the activation function. Now, what exactly does the activation function do? So it will take in all the summed values that we had from the weights, and it will have a bias term that will add so it can go up and down on the y-axis, and it's going to send a signal on to the next neuron after this one, and it's going to tell how positive or negative that output signal is going to be, and that turns into the new input signal to the next neuron. And this is very similar to how the biological terms work, where you have a neuron that sends a signal based on how strong the previous input was. If we take this analogy where a chef is trying to prepare a dish and the inputs are going to be just ingredients, the output is going to be some kind of dish that the chef makes. If we were to use only a linear regression models for our activation functions, that's like a chef just cutting up the vegetables or whatever food they have and mixing it together. That's about it. It would only be as simple as that, but it wouldn't be as good as something if they were to be slicing it, cutting it, and cooking it a little bit more. Maybe they bake it. Maybe they also do some kind of searing on it and add some seasonings to it. It's not as good as if we were to have all those other things. If we were to have a non-linear activation function, that's like doing all those mixing and baking kind of steps to have a well-prepared dish instead of just mixing up some ingredients together and calling it a dish.
And it's kind of a cosmic gumbo.
The main purpose of using these non-linear activation functions is that we can have more flexibility to help generalize our system when we're using the neural network. And there's lots of different kinds of activation functions that we can use, but I'm going to go over the 4 main ones. So to start off with, we're going to talk about sigmoid, and sigmoid's a pretty simple one to understand. It just maps any value from 0 to 1, and it's really good for displaying outputs as a percentage. So if we have after our summed values and we had add in a bias, if our input or if our value from the activation function is like 0.8, we can send 0.8 along into the next activation or into the next neuron. There is a problem when using something like sigmoid, and this is the idea of something called desaturation, where if your output value is to be, let's say 10 or 15 on one side on one of the sigmoid values, it's going to have the same output value as if something was just 1, let's say. And that diminishes the importance of the weighted values from before. So if we have something that's super important to keep track of, it's going to not take in that same value and output the same importance after that activation function. So that works on both the positive and negative side. So there's other activation functions that we can use to try to help diminish this issue that happens. So one activation function that we can use instead of sigmoid is ReLU, and that's rectified linear unit. That means that any positive value that we have, it's just going to be that positive linear value, and then anything that's negative is just going to be 0. On the plus side, the ReLU is going to map out any positive value directly on a linear unit, and that's really great for sending along information. But if we have too many negative values, it's going to create 0, 0, 0, 0 across all the different ReLUs that we have. That's going to lead to a problem called the dying ReLU problem. A way that we can fix this is we can alter our ReLU equation a little bit, and if we can have a leaky ReLU, it's called. That's where any negative value is just going to have a smaller negative value instead of actually 0. That way we can still send along some information saying, hey, this is a negative value, but not exactly 0, so we don't multiply everything by 0. We can even take this a step further with exponential linear unit. That's where we change the negative component to an exponential values. That way we can map out a little bit more accurately what's going on and have a little bit more importance to it. These are really popular in the deep learning networks. TAN-H, or hyperbolic tan, is another activation function that works similar to the sigmoid function. It maps from -1 to 1, but it still does follow the same weaknesses as the sigmoid, where if the values are way too positive or way too negative, it's not going to show as much information. These ones are really great for something like time series or sequential data, like predicting the stock market or house prices. There are other kinds of alternatives to use into these, but we're not going to be going that much into it. I think I mentioned that we were talking about 4, but I can't even count anymore. But the very last one we're going to talk about is the softmax function. Now this one works a little bit different because it is only used in the very final output layer of the network, and it's used a lot in classification models. So with this one works, it takes in all the different scores, or logits as it's called, and it's going to convert those into a percentage range out of 1. So all the values in our model is going to have each individual class labeled out, and it's going to have a value of how strong it is on a scale from 0 to 1, or it's a percentage. So for example, if we have the MNST data set, we have 10 values. It's 1 for each digit that's in our data set, and then each value is going to be spit out based on what the value, or what the model thinks it is correct. So if it thinks it's a 5, it's going to be 90% a 5, and then like a 0.01% for everything else. So mathematically, this E is Euler's number, and we take each output to this power. So this creates a really large number for large positive values and really small numbers for numbers that are close to 0 or that are negative. So we divide each number by the sum of all these other values, and this creates an output probability that sums to 1. So this function is usually set aside to the very last output layer problems, like multi-class problems, such as image recognition or classification. Having the softmax output a value from 0 to 1 is also very useful for calculating the cross entropy loss, which we'll be discussing in the next video.